here. I totally apologize for the conflicting information on that quote small. You notice it has small in quotes because there's really a small quantum physics problem. For the conflicting information there, I had started with it a problem like this, where you have lower energy or lower potential and then higher potential. And then I decided that it was just adding complication because, you can't normalize out there and whatnot. And so I intended to make it so it was, oh, well, perfect. Yeah, oops, now it's all gone. Okay, let's undo everything, just draw a new picture. I intended to make it so it was like, oh, come on. So it was like this. So you just have, you'd have like kappa 1 here and kappa 2 here if you like. So they're different constants, but you would still have exponential decays on both sides and oscillating in the middle.
Right. Yeah.
But I will grade it based on whichever way you interpret or, as long as you took something that's reasonable. And I believe Chris said that you guys did opposite things. That will be fine because no one can read a mind. I believe that anyway. I don't believe in ESP. All right. And Chris asked me a question about the test. Did you have any further comments, or Indy, did you have any questions about the test? I haven't graded yet, but hopefully tomorrow.
Nothing that specifically comes to mind. I guess on the question about the commutators,
Yeah.
how in depth did you want us to be on that answer? Like,
Well,
can we just give like the definition of commutator and kind of like a short like?
Oh, okay.
This?
The knowledge question about the commutator, not the short problem one or small problem one. Okay.
Right.
Yeah. What I was looking for that was simply looking at the difference in the order of the operators. What difference it makes if you change the order. That's what I was looking for.
Sweet, that's fine.
That's fine. My answer is consistent with that. Good. All right. Now, of course, we should have Chris do the lecture from here on in because it's just math today. You ready, Chris? Hilbert space. I am not a mathematician. You might have noticed the little snarky comments in the footnotes about mathematicians versus physicists. Did you see those? Because we use math all the time, but we don't talk about math like mathematicians. We're not pure mathematicians. And so to a physicist's mind, or at least to my mind, Hilbert space means the types of problems that we do in quantum physics, where our wave functions are in quantum physics. That's it for us. So we have n-dimensional Hilbert space or infinite dimensional Hilbert space. Yeah, that's where our answers are, and that's where we go with it. But there are definitions for Hilbert space. He says technically it's a L2, what was it, subscript A comma B or something like that. It's a Banach type of space. Those are words that don't mean anything to me. Indy's with me there. Doesn't mean anything to him either. So Chris, Banach space, is that like you totally dig that, or?
If I knew what it was.
Okay. All right. So we're all kind of equal on that. We can take the physicist view of math is a very fundamental and important tool, but we haven't gone through and proven the aspects of the math. So here I have just a couple. First of all, we're looking at chapter 3, 1-2, and appendix A, 1-2 here today. Just getting some beginnings of the math that we use in quantum mechanics. We've already done a fair amount of quantum mechanics. Now we want to step back and say, okay, so what is this math? And then we're going to dive back into it some more, doing math and not worrying about what it means. So I showed you this a long time ago, that bracket notation. Bracket short for bracket. And a bra x and a ket psi means psi of x. And this here, bra psi, ket psi, means that we have taken the integral over all space of psi star psi. So the bra here means that we're going to do a complex conjugate of that one. If you put them together, it implies the integration. And so those are some nomenclature things that are going to take on, that's the calculus meaning for the nomenclature. There's also vector math nomenclature or meaning for the same nomenclature. So in vector math, this is going to mean a column vector. And this will be a row vector. And so if you multiply a row vector by a column vector, that's going to give you a number. And so the notation works for both using calculus and functions and using linear algebra. So quantum theory, what we've already started with, is based on wave functions. How do we find a wave function so far?
By solving the Schrodinger equation.
Yeah, by solving the Schrodinger equation, which is a wave equation. Now we're going to see, like by Friday, that we actually can find wave functions from any operator eigenvalue relationship. It's not just the Schrodinger equation that we can find a wave function from, but the Schrodinger equation is the one that gives us everything. And then we had operators. What's the purpose of an operator in quantum mechanics?
To get information out of the wave function.
It's to get that information out. You get the observable information. So an operator acting on a wave function should give you the value for an observable thing like position for that wave function. So now mathematically, wave functions are vectors. Operators are matrices. So we're going to be looking at some matrix math and linear algebra ideas when we do that. So our wave functions will either be functions that as we have used or vectors. Operators, a kind of function that operates on a function, or a matrix. Some vector properties that I don't think takes any time for you to wrap your mind around is a commutative property. If I add two vectors, I should get a third vector. So that's where the alpha plus beta is equal to gamma. Two vectors add together gives you a third. And it doesn't matter what order you add them in. The associative, well, it really is, it doesn't matter what order you add them again, right? I grouped this, so I did the B plus gamma, or beta plus gamma first, and then added alpha, or the alpha plus beta first, and then add the gamma. It's going to give you the same answer. Doesn't matter what the order is of your operations of adding. And then finally, the distributive is the last one. The textbook has a few more. Distributive property, if I have a constant multiplied by alpha plus beta, it's the same as the constant times alpha plus the constant times beta. And it gives me a new vector again. Anything there that's anywhere close to interesting? Yeah.
Nothing new.
Yeah, nothing new. Nothing that you're like, oh, really? That's the kind of space we're working in? Okay, so far, everything's good. Now, what is a Hilbert space? This is the definition. The Hilbert space needs to be complete. Complete means it spans all space. And when I say it spans all space, to me, that just sounds like a few words that came out of my mouth that are some kind of jargon. And so I like to put it into a more commonplace of I can describe, and I used this at the very beginning of the semester, if you recall. If it spans all space, that means I can make a vector that's a linear combination of each one of my individual eigenvectors to take me to any location. There's no missing locations, places I can't get by taking this much of this vector and this much of this vector. And so if you read, I don't know if you read the textbook, you might have. If you read the textbook, he talks about holes in the space. And what he means by holes in the space is you can't get there. And then he takes some examples like if you take all real numbers, there's no holes. There's no places you can't have a landing spot in all real numbers. But if you take all rational numbers, there are holes. There are lots of places, there are lots of irrational numbers. Today is pi day. Pi is an irrational number. That means you can't refer to it as a ratio. As much as a kid we learned 22/7 was pi. I don't know if you learned that. It's not. If 22/7 was pi, it'd be rational, but it's not. And so all rational numbers is going to leave some places that you can't get. And so that's what we mean by it spans all space. Now, the second one is an inner product. It's an inner product space. And I'm like, what does an inner product space mean? I'm still not sure what an inner product space means. I hate to be mathematically naive, especially with a math major here. But here is how we do an inner product in quantum mechanics. In three-dimensional space, we called it a dot product. You guys comfortable with dot products?
Yeah.
In layman's terms, right? So when you're taking general physics and the teacher's trying to explain a dot product to students who've not taken any math, what do they say for a dot product?
Alpha times beta times the cosine.
Okay, that works. That's giving you the magnitude because you're multiplying the parallel components of vectors, right? You can't just multiply vectors, but the dot product or the inner product is multiplying the parallel parts. And so we call the Hilbert space an inner product space. And one of the things that our textbook says about the Hilbert space is you have to have all of your functions that exist in the Hilbert space are square integrable. Once again, what in the world does square integrable mean? What that means is you have to, for any A and B, be able to do this and get something finite, which was really important for us with our quantum mechanics. That was a defining thing about our solutions. They had to be normalizable. And so if this gives you a finite answer, it's going to be normalizable. You can multiply it by a normalization constant. And so that kind of is an important aspect of our Hilbert space. All of our wave functions have to be normalizable. So quantum physics falls in Hilbert space. And then I have, that is what I have here, the set of all square integrable functions. I should read what I have written in front of me. I was thinking, I wrote this the first time and I had something else down here. I removed it because I didn't have space for both. A very common example of a Hilbert space is Euclidean space. What is Euclidean space?
Three-dimensional Hilbert space.
Very good. There's your three-dimensional Euclidean space. That's what we live in. That's everything that you learn until you start taking crazy math classes is Euclidean space. So all of the geometry you learned in high school, that's Euclidean geometry. Chris, he'll have the opportunity to learn other kinds of geometry if he so chooses. So that's our space we're working in. Now, operators, and I spent a lot of time last night with self-doubt and worry just with this slide right here. Hermitian operators. What defines a Hermitian operator? Well, they're the kind of operators that, what's his name? Hermite? some dude was working with, and they have this property. This is, actually, no, not that. This here is not the one that defines the Hermitian operator, sadly. The Hermitian operator is defined such that the, okay, so Q operator dagger is equal to Q operator. That's what defines a Hermitian operator. But then we have to say, what in the world is that dagger? Well, that dagger means that we're finding the Hermitian conjugate, also known as the Hermitian adjoint. So a Hermitian operator is an operator where the Hermitian adjoint is equal to the original operator. Our quantum mechanics operators are all Hermitian. They're all Hermitian because our observables are real, right? That's a fundamental. Your position has to be real. It can't be imaginary. Your momentum has to be real. It can't be imaginary. And so if our observables are all real, then I should be able to say that my expectation value for some operator is equal to my expectation value complex conjugate. Right? If it's real, there's no difference in putting the complex conjugate there or not. And so here is my normal expectation value calculation, and here's the complex conjugate calculation. But when you move things from one side to the other, you actually have, let's see. Using that little caret to mean operator. When you move your operator from acting on the right one to acting on the left one, you have to take the Hermitian conjugate of it. And so this here doesn't have the Hermitian conjugate written there because it got there a different way. And that requires that you have your Hermitian conjugate is the same as your original. Now, all of that is pretty unclear, I'm guessing. If that's clear to you, then I did far better than I expected. So what I want to do, that was my best effort at doing a dagger, was to go through this problem. This is a problem in the textbook, problem 3.5, as luck would have it. And start with this definition. For all F and G, a Hermitian conjugate obeys this, to check that out. So what does it mean to have that equation written? Well, what does this mean from everything that we've done in the past?
The expectation value of the operator.
Okay, that would be right if F and G were the same. And it'd be the expectation value in that state if F and G were, specific. So it's not the expectation value only because F and G are different. How do we find the expectation value? Because it still means the same thing, except for it's no longer named the expectation value. So how do we find the expectation value?
So it's still the integral space, orbital space of F star, Q operating in.
So it's still going to be that. And so what this equation is saying is the integral of F star Q G dx is equal to the integral of q dagger f star g dx. All Hermitian conjugates are going to obey that relation. Now it says to find the Hermitian conjugate of x, I, and d dx. So let's start with x. So if I'm going to use my operator is x, I would have this would be x operator What is x operator? X, right. That's why I wrote it that way the first time. And so now I'm going to replace what I can. And then I say, what is x dagger going to have to be? I shouldn't use the same color. What is x dagger going to have to be to make these two equal each other? It's just going to have to be x dagger is equal to x. And so that is a Hermitian operator because x dagger is equal to x. That wasn't overly difficult. The next one. This one's going to introduce something that's a little more confusing. The reason it's confusing is when we come back to the relationship of moving it from I should be more fundamentally clear. If it's in the bra, you're doing the complex conjugate. And so this here, my I dagger star, it's actually got to have the complex conjugate there because of where I moved it. So that complex conjugate is going to change things. What does the complex conjugate change? It becomes negative. And so what I'm going to have here is that I dagger is equal to minus I, whereas I itself was I. So that's not Hermitian.
So,
Go ahead.
What in this is the Hermitian conjugate? Like, is it finding what I dagger is? Is that what the Hermitian conjugate is? Or?
Sorry, I had another thought that I wanted to write down. The point of this is actually for us to get a little more. By the way, this one here I didn't write correctly. The point of this is to get a little more comfortable with what it means to be Hermitian. And so what it means to be Hermitian is that the Hermitian conjugate, which is calculated by doing this calculation, is equal to the original operator. So the point of the exercise right here is to identify this is what it means to be Hermitian, and this is how you determine the Hermitian conjugate or the Hermitian adjoint. When we get to matrices, it's a lot easier to calculate the Hermitian conjugate. You take the complex conjugate of the transpose. It's a lot easier calculation. I just looked at the time and I am out. Doing the derivative, you have to use integration by parts to do that one. And it actually comes out pretty simple. I will just refer you to, remember I gave you a link at the beginning of the semester. It's in your, I think, syllabus where it works out the solutions. Go ahead and look at the solution there for problem 3.5. And he does the integration by parts really quickly. You'll want to look at the textbook's example doing the momentum operator. Let's see if I can find where that page is. 97 possibly. Yes, 97. On page 97 there, the work there for equation 319, it shows doing the integration by parts, and it has the part where there is no integral, has limits of infinity and minus infinity, and then it just disappears. And notice it has the star there in the second integral, the complex conjugate part I was just mentioning. The term that disappears, the one with the limits of infinity minus infinity, is because our functions have to approach zero at plus or minus infinity if we're in Hilbert space, right? Because they have to be normalizable. And so that's why the first one just disappears, because by virtue of being in Hilbert space and having limits at infinity minus infinity, those two terms had to be zero. So that equation 319 will help you to understand the work that's done in that homework solution site on problem 3.5. Okay, so I will try to figure out how we can do the Tuesday at your time, 9:30 to 10:30. All right, and I will be putting up a homework assignment probably by Friday that's just a bunch of math to go over this. Probably by Friday, definitely by Sunday.
Okay. Thank you.
Yeah. See you guys.